Today's lesson is on difference of squares, and we're doing a factoring summary. Okay, let's look at these two binomials being multiplied. We're going to expand them and see what we get. Now, normally when we expand two binomials, we would get a trinomial. Okay, so x plus 3 times x minus 3. This equals x squared minus 3x plus 3x minus 9. X squared, middle term, when we collect the like terms, becomes 0. And we have negative 9. Second question, x squared minus 5, 2x minus 5 times 2x plus 5. This equals 4x squared plus 10x minus 10x minus 25. Collect the like terms, 4x squared minus 25. Now, the interesting thing you'll notice is that since our middle term, one is a plus, one is a minus, the middle term becomes a 0. And so instead of producing a trinomial, we actually get a binomial. Now, this type of expansion and factoring, this is called a difference of squares. Now, remember perfect squares? Perfect squares are just numbers, terms, or variables multiplied by itself. So for example, I could have x times x. This is equal to x squared. That's a perfect square. If I had a number, 5 squared, this is equal to 25. Or I could have a term, x minus 5 all squared. When it's expanded, x minus 5 times x minus 5. Also a perfect square. Now, in terms of numbers, our perfect square numbers, the first couple would be 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and it goes on. So I have 1 squared, 2 squared, 3 squared, 4 squared, all the way to 10 squared, 11 squared, 12 squared. Now, because these are special trinomial or special expansion ones, let's examine what we have. I'm going to look at the factored form, and I'm also going to look at the expanded form. So when we look at the factored form, we see that these are in brackets. And inside the brackets, we have the same numeric value. So 2x, 2x, a 5, and a 5. But the difference is we have one operation that is addition, and an operation that's subtraction. In the expanded form, we are supposed to have a trinomial, but it's not quite a trinomial. When I say it's not quite a trinomial, it's because our b term is 0. And so our resulting trinomial is actually a binomial. One thing you'll notice also is because our first term was created by 2x times 2x, we have a number that's a perfect square and our variable is a perfect square. The last number that's produced, we had 5 times 5. Once again, this is also a perfect square. So A and C term are perfect squares. Lastly, you'll notice that in all of our expanded form of difference of squares, the C term is negative. The reason that it's negative is because we have one positive and one negative, and so we'll always have a negative C term. Now, if we recognize these three things in our expanded form, then we can go backwards to throw it into our factored form. So let's write that down. So your questions, is B equal to 0? Is C negative? And are A and C perfect squares? So if you answer yes to all of these, then we know it's a difference of squares. What you would do, you would take, now your bracket would be the square root of the A term. Then we could have square root of the AX squared plus square root of C, and we would also have square root of AX squared term minus square root of C. So those are the two brackets. Let's do a couple of these. Now this one, I'm going to do it the old way, the way we factored trinomials. Really, this is x squared minus 0x minus 36. Two factors of negative 36 that can add to 0. We would have x minus 6 and x plus 6. Okay, so this was factoring this like a regular trinomial. But we can also see that when we have a difference of squares, we could use the shortcut. So answer the questions. Are A and C both perfect squares? Yes, it's perfect squares. Is the C term negative? Yes, this is negative. Is the B term 0? Yes, we don't have a B term. Now, since we answered yes to all of these, we could use the shortcut. We're going to take the square root of the A term, square root of the C term, and throw it into brackets with opposite operations. So we have 3x minus 5y and 3x plus 5y. Same thing here, 100 minus x squared. Now, even though x squared, which is usually our first term, is written at the back, we could still consider this an A and a C. Now, because both of these are perfect squares, we can throw them into our bracket with the square roots. So 10 plus x, 10 minus x. Now, if you really wanted to make this our A term, we could factor it. So we would have negative 1 times x squared minus 100. Well, I guess we should first write it as negative 100 plus x squared, and then we can rewrite it as negative 1 times x squared minus 100. X plus 10, x minus 10. So these are two different ways. It will give you exactly the same answer, just written differently. Okay, last example on this slide. 18x squared y minus 8y. Clearly, this is not a difference of squares because a and c are not perfect squares. So if I don't have a perfect square, I'm going to see if I can take out anything that's common. 18 and 8, 2 is common. Y is also common to both. So I'm going to factor out a 2y. Okay, so factored out, I have 9x squared minus 4. Inside my bracket, I do have a difference of squares now. Perfect square, and it's a subtraction, so it is a difference. So we have 2y times 3x plus 2, 3x minus 2. Okay, so let's do an example of a few that are a bit trickier. We have perfect squares again, but now we have a few more variables. Let's factor them. 4xy minus 7z. Then we have 4xy plus 7z. Right, 9x squared plus 4. Let's check our criteria for a difference of squares. Is this a perfect square? Yes, these are perfect squares. Is it missing a middle term? Yes, it's missing a middle term. Is the c term negative? No, the c term is a positive 4. This one I can't factor. It's not a difference of squares, and it has no common factors. Okay, sometimes we'll have a fraction. If a fraction has a denominator and a numerator that's a perfect square, then the whole fraction is a perfect square. Let's simplify this. So square root, I would have 7 over 8 and x to the power of 2. So just a side note, x to the power of 4 is a perfect square because x to the power of 4 is equal to x squared all squared. Okay, so coming back to this one, I'm going to add 9 over 5y, and then we're going to do it again for the second bracket. Once again, this one, we do have two perfect squares, including x to the 4, because x to the 4 is x squared squared. So let's take the square roots and place it into our brackets. 4x squared plus 1, 4x squared minus 1. But we're not finished in this one, because 4x squared minus 1 is factorable. So since this is another difference of squares, we're going to have to continue. We're rewriting the first term, and then the second term, we're going to factor. So 2x plus 1, 2x minus 1. Slides 6, 7, 8. Try these on your own. Pause the video and I will post the answers shortly. Okay, solutions to the first one. Solutions to the second. And finally, answers to the third. Be careful, especially of the ones where you have to do more than one step. So we've learned 3 different types of factoring now. We did simple trinomial factoring, complex trinomial factoring, sorry, that's one type. We've done difference of squares, and we've done common factoring. So if we were to throw all of those together, what should we do first? First thing we should do is always look for the common factor. Factor it out if there is, and then we're going to see if we could do another type of factoring. So the question we ask ourselves, how many terms are there? We're able to factor things that have 3 terms or things that have 2 terms. Now, if it's a trinomial, we would have an equation like that. Sometimes we have a is equal to 1. Sometimes we have a is not equal to 1. So simple trinomial, complex trinomial. The 2 methods that we learned is we could do decomposition or we could do trial and error. Choice is yours. Now, if it's 2 terms, we need to check if it's a difference of squares. If it is a difference of squares, then we simplify it like that. If it's not, you might have just done the common factoring and that's it. Right, the next slides, you're going to practice some of these questions and I will post the answers for these 4 slides shortly. Okay, here's the solutions for the last 4 slides. I just want to remind you that all of these will involve different kinds of factoring. So using the flow chart from here could be very useful. Okay, the second slide of practice questions, answers to the third slide of practice questions, and the last slide of practice questions. Okay, so that is it for today's lecture.